All right, algebra friends, algebra 2 friends, here we are looking at parabolas. And I know we've talked about parabolas before, but here we're going to talk about them in the context of what we call conic sections. And excuse my screen, I kind of had some trouble with the sizing. So some things look ridiculously large and some things look crazy small. So we're going to talk about a parabola. We're going to talk about what a conic section is. We're going to talk about parts of a parabola that are called the focus, the directrix, and the latus rectum. And so the best way to do this is to look at a figure. So I have a figure down here. Conic sections, the second vocabulary term, refers to the idea that the things that we're going to study in this section come from what we call a double napped cone, or if you would think about a line, let me get my pen, if you would think about a line rotating, this line here rotating around this point, kind of, like, and so one, if it goes around this way, this part would go around this way. Is that kind of, can you kind of visualize that? Okay, and then if you would slice it in different ways, so if you have a plane and it slices through, or you get the cross section when the plane is parallel to this line at a particular stopping point, right? So if this plane would be parallel to the line here, this plane is parallel to this line, we get a parabola. When the plane is perpendicular to the axis, right? Let's call this axis of rotation in a way. When the plane is perpendicular to that axis of rotation, you get a circle. When the plane is neither parallel to the side nor perpendicular, but having some other angle, we get what we call an ellipse. And when the plane is vertically slicing, we get like these two shapes here. You can't really see it, but these two shapes here, that is a hyperbola. So when we talk about a parabola, we're going to be talking about parabolas that are like this and like this and like this. When we talk about a circle on the XY plane, we'll be looking at circles like this. When we talk about an ellipse, they're kind of like oblong circles with special properties. Talk about their properties. And when we talk about a hyperbola, we're going to be talking about hyperbolas kind of look like this on the X and Y axis and all. So that will be one hyperbola, and this would be a different one, this one in blue. So these are the shapes that we talk about when we refer to conic sections. So now these words down here are going to refer specifically to the parabola. All right, so conic section is just what is like the overarching idea of what we're going to be talking about. All right, so now this is what I mean, ridiculously big. I'll do better next time. Let's make this a little bit smaller. So we have this beautiful concept. So we talked about a parabola as just the graph of a quadratic equation. Totally fine. Now we're looking at the structure or the geometry of a parabola. The geometry of a parabola tells me, let's get a marker here that's a little larger, tells me that there's a point and a line. Here's the parabola right here. I'll highlight it in red. Here's my parabola, just so things look kind of comfortable. And so if I geometrically think about this situation, there's a point inside the parabola and a line outside the parabola that is referred to as the focus and the directrix. The way these two things relate to the parabola is that every distance, or every point on the parabola, is of equal distance from both things. So obviously the vertex here would be equidistant from the focus and the directrix. But like if I were to pull a point here, let me use a different color to differentiate. If I were to pull a point here, if I measure this distance, right, from the focus from here to here, and I measure the perpendicular distance, perpendicular means going straight down, making a 90-degree angle down here, these two distances are going to be the same. And so that's what you're seeing here with this dotted line and this line. So whatever this point is here, the distance from here to here and the distance from here to here has to be the same. That is what the focus and directrix is. So it's a very specific thing. So if you take the collection of all the points that are equidistant from this point and this line, you would get the parabola. I'm going to say it again. If you take all of the points in the world that are equidistant from this point and this line, what you create is a parabola. Well, okay, in two-dimensional, because three-dimensional would be a whole other thing. Okay. So that kind of takes care of those two concepts, the focus and the directrix. Now we're going to look at the latus rectum. So the latus rectum is going to refer to this right here being the focus, right? We talked about the focus just now. Here's the directrix. The line that goes through the focus and that intercepts the actual parabola, that segment is going to be referred to as the latus rectum. Does that make sense? Okay, so the endpoints of it are going to lie right on the parabola, and so that's the other thing that we need to know. And we'll talk more about this as we get through some examples. So we have another way of looking at this idea of what a parabola is. We talked about, and I may have I don't know, I won't say I misspoke. I think different textbooks really do use different words. This is the generic formula or the general formula of a quadratic equation that's going to give us a parabolic graph, right? Ax squared plus bx plus c. And sometimes I call it standard or general, and I think I've heard it in some books called that way. Let's call it general for now, because they're referring to this in our textbook as standard. I would call this vertex form, and other textbooks use it differently. That's fine, who cares? But here, when they refer to as standard form of the equation of a parabola, they have it in vertex form. I like to say vertex form because it's very descriptive of what I have. If I have this situation, I literally have the vertex of the parabola, and it will be located at HK. All right. So for instance, if I had an equation y is equal to 3 times x minus, or let's say x plus 1 squared plus 7, I literally can look at this and tell you that the vertex is -1 comma 7, because the formula tells me to minus h, and what would I have to minus in order to get a plus 1? It will be a -1, right? So minus 1, 7 would be the vertex, and I can do that just by looking. That's why calling it vertex form is convenient, because it reminds us of what we have. Given that h is going to be the x term of the vertex, it also makes sense that x equals h, that vertical line, is the axis of symmetry. That taken care of, we need to talk about how to move from one direction to another. How do you move from general to this form, or this form to the general form? To move in that direction, you would just square this, x minus h times x minus h, FOIL it out, multiply by a, join like terms together, and you would get this form. And when you got that form, you would realize that a has the same value as it did before, the same indication as before. If a is greater than 0, we know that we have a happy parabola, and the vertex is a minimum. In this case, the k value for the vertex is going to be the lowest that graph can go. And if a is less than 0, we get a maximum value, get a sad parabola with a max value, where the k value, that y term, is as high as the parabola will go. So let's use this information to take a look at this next situation, example 1. We're going to analyze the equation of a parabola. We're going to write this in standard form, and when they say standard form, they're talking about vertex form. And then we're going to identify the vertex, axis of symmetry, and the direction. Shouldn't be too bad. We can do the direction now, but let's go ahead and do what they asked us to do. In order to write it in vertex form, let's remember what vertex form is, or as they call it, standard form. A times x minus h quantity squared plus k. What you notice is you got a perfect square in here. We're going to need to create a situation where we have a perfect square trinomial. I will show you how to do this. So we start off with the equation y is equal to 3x squared plus 24x plus 50. And so what I'm going to do is I'm actually going to, there's a couple ways to do it. I'm going to send the 50 over to the other side just for safekeeping. So y minus 50 is equal to 3x squared plus 24x. And now what I'm going to do is I'm going to factor out the 3. And I have to factor it out. Even if 3 couldn't go into this number, in order to do this, I have to factor it out. Definitely, I got to pull it out, because I need to make sure that when I do the next part, I am dealing with a coefficient of x squared that's 1. So just stay with me on this. So I got that, and I have y minus 50 equals that. All right, does this make sense so far? I just pulled out the 3, and I just said even if I couldn't really factor the 3 out, this was like 17, I would still put the 3 out, and I just have 17 over 3 here. Like I have to do it. Okay, so now the next point is that we're going to complete the square. You remember completing the square? You take the b term, you cut it in half, and you divide it by 2. And you add that to both sides. So let's go ahead and do that. So when I do that over here, b term is 8, cut it in half is 4. I'm putting a 16 over here. You remember what you do to one side, you do to the other. But I did not add a 16 to this side. That's the thing you need to keep in mind. I didn't. I know it says plus 16, but really overall what's happening is I got to think about the fact that this is 3 times whatever I have here. So by having this inside of the parentheses, I'm not adding 16, I'm adding 3 times 16. Hold on to that concept. Make sure that makes sense. So now instead of adding that, I have to this side, I have to add a different number. And the different number is 3 times that, which is 48. So 3 times 16. So technically I added 48 to this side. So now when I simplify this, let me get out of this crazy color. Now when I simplify this, I get y minus 2 is equal to 3 times, factor this, x plus 4 quantity squared. You see we're almost there. Do you see we're almost there? You see it. I'm going to move the 2 back over to the other side. By the way, sometimes people have this form of an equation. You might see in a different textbook, y minus k is equal to a times x minus h quantity squared. So technically in some textbooks, vertex form is this. I'll honor our textbook and put their standard form the way they want. Let's throw the negative 2 over to the other side. So we get y is equal to 3 times the quantity of x plus 4 quantity squared plus 2. Make sense? I hope so. Let me know if it doesn't. So I did the thing. I'm sorry. We did so much work. I was like, this is great. I'm done. No, I'm not. So the first thing we need to do is identify the vertex. The vertex is going to be at negative 4, 2, right? Minus a minus 4 gives me that, minus h gives me that, plus 4 gives me the minus 4 gives me blah. Good. And then the axis of symmetry, A of S, is going to be x is equal to negative 4. And then we know that my parabola, the A value is greater than 0, so it opens up upward. We have a minimum value, min value at axis to directional open. They didn't ask us for the min value, but we have a min value at 2. So that's as low as it will go. All right, so graphing parabolas. So as we look at these, this new way of looking at a parabola, we can consider the vertex form and all of that stuff by looking at our parabola through that lens. So remember vertex form, or I'm sorry, standard form they call it, a times x minus h quantity squared plus k. If you look at this, you can see that, well, x minus h, what's being subtracted here? Nothing, 0. What's being added? Nothing, 0. So I know that I already have a parabola with its vertex at 0, 0, right? Then I know it's sad, and so I know that it is going downward. And I've talked to people about this before. When we have a typical parabola, like the parent graph, it goes out 1, up 1, out 2, up 4, right? Out 1, up 1, out 2, up 4. Just, y equals x squared. And if I throw a 2 in front of that, it's just going to stretch it by 2 vertically. Same thing's happening here. So this goes out 1, not down 1, but out 1, down 2. Out 2, down not 4, but down 8, because it doubles the stretch in a negative direction. If that doesn't make sense, no problem. We can go ahead and do an XY chart and just rock it that way. And we only need to do 2 points on one side because we can reflect them over to the other. So if I were to plug in, let's say, -1 and -2, when I plug in -1, I get a -2. And when I plug in -2, I get a -8. Okay, and then that same thing would happen, no 0 is 0, that same thing happens at 1 and at 2, and that's just me exploiting symmetry. And so I get a -8 here. I hope this is making sense. Please let me know. Please let me know. Don't stay quiet. Okay, So we have 1, 2, 3, 4, 5, 6, 7, 8. Let's go down 8 there. And then so I see at 1, I'm